Hey, and welcome back to Quantum Mechanics for the Working Professional. This is a third video in our series of problems and solutions associated to Section 1. By the way, if you haven't yet found the exercises or forgot where they are, they're at the end of our lecture notes for the Section 1 Stern-Gerlach experiment. Today, we're going to be looking at problems 5 and the first part of problem 6. Specifically, we are asked to consider two different quantum states given by column vectors 1, 1, and 1, minus 1, called phi 1 and phi 2 respectively. And we are to argue that phi 1 and phi 2 form an orthogonal basis of states in our vector space of quantum states for the two-level system, which is, again, meant to model things like the silver atom, stuff with spin up and spin down. And then we're supposed to argue something about defining the probabilities and so on. So we'll get into all of that as we proceed. So without further ado, let's get started. Okay, so the first thing we should probably say is that a two-level system representing an atom with spin states, right, like a spin one-half particle, like a silver atom or an electron, things like that, don't particularly care about the orientation of the magnet, say, from the Stern-Gerlach experiment. They are spin up or spin down regardless. It's still a question, as we mentioned in the lecture, of data storage. They can only store one qubit, if you like, either up or down. But we can measure that state up or down in the x direction, in the y direction, in the z direction, however we orient our magnet. And so different values of alpha and beta, those constants that parameterize a generic quantum state, correspond to different kinds of measurements, to measuring the spin, say, in a different direction. And again, all of this will be made clear as we proceed into the material and learn about complex numbers and learn about the spin algebra and so on. But I'm just throwing that out there so at least to pick your interest and to kind of hopefully motivate why we're bothering to look at all these different vectors. So to that end, recall that a generic quantum state for a two-level system is given by the vector or ket psi, and we parameterized it with two constants, alpha and beta, where alpha multiplied up and beta multiplied down. And we represented this as a column vector, alpha and beta. Now, we are asked to define two specific values of these parameters, namely the vector phi 1, given where alpha and beta are both equal to 1, so 1, 1, and phi 2, given where alpha and beta are both 1, except for beta is negative, right? So that's 1 and minus 1. So the first thing we need to do is understand how these two states behave when we take inner products of themselves, right? Because we already know, for example, that up with phi 1 is going to be given by what? What is that? Well, that's up with 1 up plus 1 down, which is just up with up, which is just 1, right? And similarly, down with phi 1 is also equal to 1, right? They are not orthogonal states. We have done those kinds of calculations extensively when we studied problem 1. So now let's look at a different situation. Let's ask, what is the inner product of phi 1, the bracket of phi 1 with itself? So by now, hopefully you're experts on this. This is 1 with 1 and 1, 1. Multiplying these two things together, we find 1 times 1 plus 1 times 1, which is 2. So evidently, phi is not a normalized state. Similarly, we can compute phi 2. 1 minus 1, 1 minus 1. And we see here that the minus signs multiply each other. 1 plus minus 1 times 1 equals, again, 2. Good. Again, phi 2 is not a normalized state. Finally, we can look and ask, what is phi 1 with phi 2? Phi 1 with phi 2 is 1, 1, and 1 minus 1. And now we see where the minus signs come into play. That's 1 minus 1 is equal to 0. So in other words, phi 1 and phi 2 are orthogonal states. The projection of phi 1 on phi 2, if you like, is 0, just like up is orthogonal to down. So we have found two orthogonal vectors, and therefore we have a basis. Incidentally, if you want to normalize those states, right, the easiest thing you can do is consider 1 over the square root of 2, 1 and 1, and 1 over the square root of 2, 1 and minus 1. You can call these, phi 1, I don't know, tilde, 2 tilde, if you like, to represent the fact that they are normalized. We will do a lot of normalization in further lectures, and we talked a little bit about normalization in the previous exercise. So just so you know, these factors of 1 over square root 2 are going to show up a lot. Anyway, moving on. So now that we know how to deal with this new basis of states, we can represent our generic quantum state psi in two different ways. We have, of course, the classic alpha up plus beta down. But now, because we have two different orthogonal basis vectors, we can reparameterize psi in terms of, say, two other constants. Let's say gamma and delta, gamma phi 1 plus delta phi 2. Big deal, you might say. Yeah, fair enough. Couple points worth making here. Alpha and beta are related to gamma and delta. You can think of alpha as a function of gamma and delta, and beta as a function of gamma and delta, or vice versa. They are both just different ways to parameterize a generic quantum state, and we will use both in what follows. So for the second part of problem 5, we are asked to compute what is the probability of observing a generic quantum state, say psi, in the state phi 1. So suppose we had a detector that could measure whether or not the silver atoms were in the state phi 1 or the state phi 2. Maybe this corresponds to spin in the x direction, say, instead of the z direction. Hint, hint. So let's find out what that might be. So last time we already discussed, when we looked at probabilities, that the probability of finding the particle in the state psi 1, given that it's in the state psi, is given by the projection of psi 1 on psi squared divided by the magnitude of phi 1 magnitude of psi, right? We did this whole thing about the Cauchy-Schwarz inequality. That's where we got the denominator from. Good. Okay, so now we must simply evaluate the probability given here. So there's two ways we can evaluate that probability. We can evaluate it using psi equal to alpha up plus beta down, or we can evaluate it in terms of gamma and delta with phi 1 and phi 2. So let's do both. Let's start with gamma and delta. So let's say that psi is equal to gamma phi 1 plus delta phi 2. This one's just easier, right? So phi 1 with psi is just given by phi 1 gamma plus, that's right, 0, because phi 1 with phi 2 is 0. Good. So this is just 2 gamma. Okay. Now, we know that the magnitude of the phi 1 vector is 2. We don't have to do that calculation again. So all that remains to compute is phi with itself in these new variables, gamma and delta. So let's do that. So phi with itself is given by the bra phi 1 gamma plus the bra phi 2 delta. And again, we're going to learn about complex numbers in the future. For now, I'm not really dealing with gamma and delta as complex numbers. I'm treating them as real numbers. For those of you who are really worried about complex conjugates, we'll get there. We'll get there, but not yet. Okay? Everything's fine. So now multiply this by psi. Good. So now we have gamma phi 1 on psi plus delta phi 2 on psi. So we know that phi 1 on psi is 2 gamma. So that's 2 gamma squared plus delta times, well, what is that? We know that phi 1 with phi 2 is 0 and phi 2 with phi 2 is 2. So this is delta squared times phi 2 with phi 2, which is, of course, just 2. So phi with itself, in terms of gamma and delta, is 2 times mod gamma squared plus mod delta squared. Great. Okay, so now let's put this into the final formula. So the probability of finding the state psi in the configuration phi1 is given by absolute value of 2 gamma squared divided by 2 times mod gamma squared plus mod delta squared. Those factors of 2 all cancel each other out, and so we're left with something that looks very familiar. And hopefully, symbolically, this makes sense because we just kind of relabeled things in a different way. Sure, there's factors of 2 floating around, but that was almost a little bit of complexity to make the problem more interesting, right? So, hopefully, by all the the symmetries and notational parallels that you've seen so far, it's not hard to convince yourself that P of phi 2 is given by mod delta squared over mod gamma squared plus mod delta squared. And again, P phi 1 plus P phi 2 is equal to 1. That is to say, there's a 100% chance of finding it either in the phi 1 state or the phi 2 state. Great. To see something really interesting, we need to redo these calculations in terms of alpha and beta. And this will kind of give us a hint of what's going on with this change of basis. So let's start that way again. So let us recall that the probability of finding the particle in a phi 1 state is given by phi 1 times psi divided by phi 1 squared psi squared. But now we're going to use the other representation of psi, psi equal to alpha up plus beta down. All right? Now we can go back to our column vector notations for this. So this is just alpha and beta. And in that context, right, you might recall that phi 1 is just 1, 1. Awesome. Okay, so let's proceed. So phi 1 on psi, in this case, is just 1, 1 times alpha beta, which is just alpha plus beta. Easy enough. Since we're here and doing this calculation anyway, let's go ahead and do phi 2 with psi. That's just 1 and minus 1 with alpha and beta. And that's just alpha minus beta. Okay, good. So far, a little different. And this is where it's going to get really fun. So, plugging this back into our formula here, and remembering that that is just 2, and that is just mod alpha squared plus mod beta squared, we find the probability of finding the state in phi 1 is equal to the modulus of alpha plus beta squared divided by mod alpha squared plus mod beta squared divided by 2. Right? Okay. So let's expand that out a little bit just to see what happens. So that's mod alpha squared plus mod beta squared plus 2 alpha beta divided by 2 mod alpha squared plus mod beta squared. Kind of a mess, but let's keep going. Let's simplify a little bit further. So we find that the probability of finding the state in the phi 1 configuration is just 1/2, right? Mod alpha squared plus mod beta squared canceled out, plus 2 over 2, which is 1, alpha beta over mod alpha squared plus mod beta squared. Simplifying further, getting those 2's to cancel out, we find that the probability of finding the state in the phi 1 configuration is just 1/2 plus alpha beta over alpha squared plus beta squared. Awesome. Okay, so far so good. So now let's go ahead and, just because we're here, do the same calculation for phi 2. As phi 2 is literally the same thing except for there's a minus sign, right? So that minus sign actually shows up here. So that minus sign propagates to here, which propagates to here. So it's actually 1/2 minus alpha beta over mod alpha squared plus mod beta squared. So let's clean that up and have a look and discuss what it means. So the probability of finding the state in the phi1 configuration versus the probability of finding the state in the phi2 configuration are given by 1/2 plus alpha beta over mod alpha squared plus mod beta squared versus alpha 1/2 minus alpha beta. Okay, so now let's compare these results to what we did with the gammas and the betas, right? So that was just mod gamma squared over mod gamma squared plus mod delta squared versus mod delta squared over mod gamma squared plus mod delta squared. So very different configurations. And indeed, you can think of the difference as just a question of reparametrizing. So for the specific case of, let's say, alpha and beta equal to, say, 1 and 0, say the spin up state, we notice that the probability phi1 and phi2 are both equivalent, right? Because in one case, alpha is equal to 1, but beta is equal to 0. So this term here would vanish, and this term here would vanish. Similarly, if we considered the spin down state, the probability of both of these would again be equal, and both again would be equal to 1/2, because once again, alpha would vanish and beta would vanish. So the difference in these two representations in terms of alphas and betas or gammas and deltas really boils down to what we're trying to measure, right? So if we're trying to measure something where the spin is up, say in the z direction, that is to say for fixed alpha with 0 beta or fixed beta with 0 alpha, this representation, these phi1 and phi2 don't make any sense whatsoever. But if we can find a way to measure the system in a configuration of, say, phi1 or phi2, then we can restrict ourselves to this because those observations do make sense. So what am I trying to say? The spin up and spin down configurations, those up and down cats that we discussed, are great for studying the z direction. That's how we define things. And so from that perspective, parametrizing psi in terms of alpha up and beta down makes a lot of sense when that's what we're measuring. But if we're going to be measuring phi1 or phi2, if we're measuring something totally different, then it's not as helpful. We want to actually use the phi1 and phi2 basis, because then we can definitely ascertain, well, the probability of finding it in the phi1 state is given by, 100%, that kind of thing. I realize this is a little nuanced, and we'll definitely get into more details about this in future lectures, but if anything, this was a really great exercise in computing with vectors and learning about different kinds of bases, things that we'll need a lot moving forward. Problem 6 basically says, okay, there's a state theta, which is another way to parameterize a two-level system. And let's say that theta is given by cosine theta times phi up plus sine theta times phi down, right? And so we know that theta with theta is equal to cosine squared theta plus sine squared theta, which hopefully you know by trigonometric identities is equal to 1. So, hey, theta is a normalized state. That's awesome. But also what it is, it's a one parameter family of states that can represent, if you like, a different basis for our two-level quantum system. It's a one parameter family of basis states. So we're asked to find what values of theta are phi1 and phi2. Well, if you know anything about angles, hopefully this is pretty easy. In the xy plane, we know that if we want to move x out to even, we move out by 45 degrees, because sine of 45 degrees equals cosine of 45 degrees, and that equals 1 over this, right? And that equals to what? 1 over the square root of 2, which is that number that we found earlier. So, in other words, theta of 45 degrees, which, if you like, is pi over 4, is equal to 1 over the square root of 2, 1, 1, which, if you like, is equal to 1 over the square root of 2 times phi 1. Okay, easy. Now, let's do phi 2. I'll give you a hint. They're orthogonal states, right? So let's go back to that drawing that we had. How do you find an orthogonal state? You just draw the 90-degree vector out this way, What angle is that? That's 3 pi over 4 or 135 degrees, right? 90 plus 45. So that would give us 135 degrees, 3 pi over 4 minus 1, right? Oh, no, that's not right. Oh, that's so not right. That's not right. There's a minus sign out in front. Because that gives us minus in the x direction and plus in the y direction. So that gives us that. Right? So that gives us minus psi 2. Oh well, we learned something. So how do we get rid of that minus sign? We reflect backwards. So in other words, we can go from 35 degrees to minus 45 degrees, which goes to minus pi over 4, which gives us 1 and minus 1, again with that square root of 2, which now gives us the appropriate sign. So, in other words, phi 1 is related to theta equal to 45 degrees, and phi 2 is equal to theta equal to minus 45 degrees. They're still orthogonal states. It's just reflected by 180 degrees. Anyway, this fact is no accident. The fact that that is related to also rotating the magnet in the Stern-Gerlach experiment by 90 degrees, say from the z direction to the x direction, will be something that we discuss in detail in the third section of our lectures. But first things first, we got to get there. So this is the end of problem 5 and the first part of problem 6. Thank you so much for watching. We will go into gory details about all this stuff in the future, so hold on tight. See you next time.